Hey, what's up guys? This is Dr. Vivek Palipuram bringing you the next lecturette in ECPE 127. In this lecturette, I'm going to discuss Gaussian random variables. But before we proceed any further, let's practice our integration skills. So tell me, what is the answer of this integral? Is your answer a log cabin? Well, as it turns out, this is an indefinite integral, so you need to add the constant term c into this equation. So when you add log cabin to c, what do you get? You get a houseboat. Okay. So in this class, we are going to focus on Gaussian random variables, which are one of the most important random variables in not only science and engineering, but also in our nature. They are so prevalent, they are so common, and they're so normally occurring that sometimes or most of the times, they are even referred to as the normal random variables. They are normal random variables. A Gaussian random variable x is explained by two important parameters. Its average value or mean, mu, and its standard deviation, sigma. And the probability density function of a Gaussian random variable is given by this equation right here. F of x is equal to 1 over root 2 pi sigma squared times e to the negative x minus mu whole squared over 2 sigma squared. Now, if you recall from the previous lecturette, one needs to integrate the probability density function to find probabilities of different events. Don't worry, you do not have to integrate a probability density function of a Gaussian random variable because such an integral is impossible to find using conventional methods. Instead, I'm going to give you some other simpler methods that avoid integration altogether. Now let's discuss the shape of a probability density function of a Gaussian random variable. So here are the two examples. Both of these Gaussian random variables have the same average value equal to 2, but their standard deviation is different. The very first one has a smaller standard deviation, which is equal to 1/2, which tells you that the variance is very small because variance is sigma squared. It also tells you that most of the values will be concentrated near the mean. The second Gaussian random variable has a larger standard deviation, and therefore it is going to have larger variance of data's distribution about the mean. So your Gaussian random variable is going to have a bell-shaped curve, and depending upon its standard deviation, either it's going to be slimmer and taller, or it's going to be shorter and stouter. Now, I have been telling you that Gaussian random variables are really very important. Well, they are. Let's consider an example where you're performing some scientific experiment, but it's not possible for you to get large amounts of data. So here's how typically you will construct your experiment and use it to explain the underlying phenomenon. You'll perform small set of experiments and gather small number of data values. For each of these experiments, you will construct the average values, and you'll find that these averages are going to be different, meaning they are going to be random. Not only that, these averages are going to follow the Gaussian distribution. So the average outcomes are going to be normally distributed, and that is due to an important theorem in statistics, which is the central limit theorem. The central limit theorem states that if you were to consider averages for several samples from an experiment, then those averages are going to follow a bell-shaped curve. In fact, Gaussian random variables happen to be a very reasonable assumption for many kinds of phenomena that we are trying to explain. For example, in electrical engineering, one uses Gaussian noise to test a system. In regression analysis, to construct predictive models, we assume that the dependent variable that we are trying to predict is going to be a Gaussian random variable. We are going to look into that aspect later ahead in ECPE 127. Now let's focus on the central limit theorem, which states that the averages of samples from a population are normally distributed. Now let me give you an example of the weight of individuals in the United States of America. Let's say that you're interested in finding the average weight of the population of the United States of America. Now this population has 400 million people. So you will have 400 million weight values. it is not only counterintuitive, but it is also impractical to obtain the average weight of all these individuals and use it to explain this entire population. That's never going to happen. You will not be able to measure the weight of all these 400 million people before burning yourself out. Instead, what you're going to do is you're going to construct small samples comprising, let's say, 1,000 individuals, which are easy to obtain, and calculate averages of those samples. So let's say that average of this sample is mu1, average of this sample is mu2, average of this sample is mu3, and so on, and the average of this sample is mu of n. Now, the central limit theorem states that mu, which is a vector comprising mu1, mu2, mu3, and so on until mu of n, is actually going to be a random variable. Specifically, it's going to be a Gaussian random variable with a bell-shaped curve like this. Not only that, the average or the mean of this bell-shaped curve is going to be approximately equal to the population's mean. Not only that, the standard deviation sigma of this bell curve will approximately equal to the sigma of the population, or square root of n, where n is the size of each sample. So if you were to consider sample size or the size of these individual samples as 1,000 points, then n is going to be 1,000. So in this way, you can guesstimate the standard deviation of the population using the central limit theorem. In fact, I also use central limit theorem in my own research. My students and I, we work on cloud computing, and we are also interested in modeling the performance of different cloud instances. Here, I'm going to show you an example of the performance of a very particular cloud instance of Google called Google Cloud N1 Standard 2 virtual machine. Now, for this virtual machine, we are interested in modeling the single precision floating point operations. Let me call it SP flops. So what my research group did, they benchmarked this instance to construct a population of vast number of floating point performance values. They constructed a population of 100,000 data points, and further, what they did, they constructed several samples out of it, which are the subset of these populations, each sample comprising 100 points, and they obtained the averages. So mu1, mu2, mu3, and so on until mu of n. So this random variable mu, which can be mu1, mu2, and so on until mu of n, is going to be a Gaussian random variable because of central limit theorem, CLT. So next, what they did, they plotted the histogram, and they found that it is indeed approximately modeled by a Gaussian distribution, and the average of this Gaussian distribution is approximately equal to the population average. And the standard deviation sigma of this Gaussian distribution is approximately equal to sigma of the population or square root of 100, because we are considering samples of size 100. So using this Gaussian distribution, we were able to explain the single precision floating point performance phenomenon without having to get its actual distribution, which may be absolutely totally different. And this helps us in performing further studies when we are trying to measure other performance parameters and analyzing them as a collective. So that's the power of central limit theorem. In fact, I also asked you on Slack channel to roll a die 6 times and give me the average. The reason why I asked you to do that is to demonstrate to you guys the power of the central limit theorem. Some of the students have given me the averages. Now I'm going to show you that those averages are going to be more or less different, meaning they are going to be random. Not only that, their histogram is going to be approximately a bell-shaped curve. So let me demonstrate that to you. So I rolled the die first in order to get the ball rolling, or the die rolling. So I got the average value as 3. Monica gave me her average value as 3. Cordero got 4.16. Bo got 2.83. Janet, a student from my another class, she got 2.16. Nitin, another student from another class, got 3.67. Seth got 3.5. And Harley got 2.83. So next what I'm going to do is I'm going to construct a histogram, which is a frequency table. A histogram is a good approximation of probability density function, or the PDF. And I'm going to show you now that the histogram will be approximately bell-shaped. So let me draw the histogram. On the x-axis, I have the averages. Now the averages are going to fall between 1 to 1.1 to 6. So 1, 1.5. I'll draw these different intervals. So this interval means 1 inclusive, 1.5 exclusive. The next interval is 1.5 inclusive, 2 exclusive, and so on. Let me stop right here at 5 because most of the values are under 5. And on the y-axis, I'll have the frequency. So I'll find out how many points are there in each of these intervals, and I'm going to plot their respective frequencies. Okay, so Dr. P and Monica, both of them got average as 3. So both Monica and I, we belong to this interval. So I will draw a bar here towering to the value 2. Then Cordero got 4.16, so he belongs to this interval right here. Bo got 2.83, so he belongs to this interval. Janet got 2.16, so she belongs to this interval. Nitin got 3.67, so he occupies this interval right here. Seth got 3.5, so he belongs to the interval to which Nitin belongs to. So this interval will now have 2 members. Harley got 2.83, so he will join Bo. And there you go. That's my histogram. Now carefully observe the shape of this distribution. Don't you think that it is explained by a nice bell-shaped curve? So there you go, guys. This is the power of central limit theorem, and it comes to life even when I have such a few members to explain my data. So that's the power of central limit theorem. Also recall how we can use this particular Gaussian curve to explain the underlying experiment, roll a die. We know that it's a uniform random variable, so its expected value will be 3.5, and its variance is L minus K times L minus K plus 2 over 12. So that is 5 times 7 over 12. So that is 35 over 12. So the variance of this experiment, rolling a die, is 35 over 12, which is 2.91. So that's the variance. So sigma will be square root of that. Sigma will be square root of that. Approximately 1.7. Now, the central limit theorem tells you that this Gaussian's average will be approximately equal to the population average. So notice here, it is indeed approximately equal to 3.5. Furthermore, the standard deviation sigma for this Gaussian random variable will be approximately equal to standard deviation of the population or square root of n, where n is equal to 6 here. So I can see here that the standard deviation in this case will be approximately, this is 2 sigma, because that's one of the properties of Gaussian's bell-shaped curve, that most of the values are within 2 sigma from the standard deviation. From here, even if I get the average as 3.3 for this bell-shaped curve, I can guesstimate that the standard deviation, or 2 sigma here, will be approximately equal to 2. So which implies that sigma is equal to 1 for this bell-shaped curve. So sigma of the population will be 1 times the square root of 6. So let me see what the square root of 6 is. square root of 6 is 2.44. So sigma p is approximately equal to 2.44, which is somewhat close to 1.70. And that's a little bit farther away still because I do not have sufficient points. But still here in this example, you can see the power of the central limit theorem and the power of a Gaussian distribution. So let's talk about some properties of Gaussian distribution. If X is a Gaussian distribution with average mu and standard deviation sigma, you can construct another Gaussian distribution Y, which is expressed as a linear function of X in this manner, where A and B are constants. Such a Gaussian distribution is going to have mean of Y as A mu plus B and standard deviation sigma Y as A times sigma. Now to prove this, I need to use advanced calculus concepts, which is outside the scope of this course. So I will avoid that. The next important aspect of a Gaussian random variable is its standard normal form. A standard normal random variable is also a Gaussian random variable with a very specific property that its average is going to be equal to 0 and standard deviation is going to be equal to 1. And that's why it's called as the standard normal distribution. Because of this standard property, its average is 0 and standard deviation is 1. And its probability density function takes this form right here, which is easy to obtain when you plug mu as 0 and sigma as 1. The cumulative distribution of a standard normal Gaussian random variable is obtained by integrating the PDF from -infinity to z, just like how the CDF of any random variable is obtained by accumulating the PDF from -infinity to x. So this is the form for the CDF of a standard normal Gaussian random variable. Phi is a representation for the CDF of a standard normal Gaussian. Just like any other probability density function, area under the bell-shaped curve is equal to 1. So area is 1. So that's another useful standard normal random variable. You can also express a Gaussian random variable x as a linear function of a standard normal random variable in this manner. So any Gaussian random variable with mean equal to mu and standard deviation equal to sigma is expressed as a linear function of the standard normal random variable z as sigma z plus mu. To find the probability that random variable x, the Gaussian random variable x, is less than or equal to small x, one can evaluate the standard normal random variable CDF at x minus mu over sigma. And this is easy to prove. And let me show you how. So let's say that we need to find the probability that capital X is less than or equal to small x. Now, the property of Gaussian random variable tells you that x can be obtained, or it can be written in terms of standard normal distribution as sigma z plus mu. If I were to move the mu on the right hand side and move sigma to the denominator of the right hand side, I get probability that z is less than or equal to x minus mu over sigma, which tells you the probability that z is less than or equal to x minus mu over sigma, which is obtained by finding the value of the standard normal random variable CDF at x minus mu over sigma. This particular theorem will be used to solve all kinds of probability problems with Gaussian random variable, and I'm going to show you how. Another important property of a Gaussian random variable is that it's going to have a bell-shaped curve which is symmetric about the mean, mu. So this region right here, which is shaded, it gives you the probability that the random variable capital Z is less than or equal to small z. The symmetry property also tells you that these two shaded areas will be equal. So it essentially tells you that the probability that random variable is greater than z is actually equal to the probability that it is less than negative z. So that's theorem 4.15. It tells you the probability that z is less than or equal to negative z is equal to the probability that it is greater than small z. So these are the theorems which will be useful to calculate probabilities of different events with respect to a Gaussian random variable. I think it's a good time to stop this lecturette right here. So this lecturette introduces you to Gaussian random variables, shows you the power of central limit theorem, and it introduces you to some theoretical concepts with Gaussian random variables. In our next lecturette, I am going to show you how to solve probability problems with Gaussian random variables. In the meantime, here's what you can do for fun. Why don't you ask your friends to roll a die 6 times and get their averages? You can do that over the Slack channel. And try to draw the histogram. I challenge you that you will not get a distribution that is away from a bell curve. Or essentially, you will get a distribution that you will get a bell curve. If you do not get a bell curve, I'll give you 100 grand.